when you start.
Yes.
Good. All right, Micah, don't watch this until after you complete your exam. All right, so number 12. So that is a large carbon molecule with C12, 12 carbon units. So we've got 12 carbon. How many hydrogens?
22.
22. And how many oxygens?
11.
All right. Can you find me the atomic mass of carbon? Open your textbook and then memorize it. It will save you time. Carbon, oxygen, and hydrogen are ones you should memorize. 12. Carbon is 12 atomic mass units. Hydrogen, 1. And oxygen, 16. All right, so what's the weight of oxygen? Sam? How much does oxygen weigh? Whatever Harper talks, you should learn to listen. 16. How much is Levi? How much is hydrogen?
1.
All right. So I would multiply these out. 12 times 12. 22 times 1. And 16 times 11.
176.
So can someone add these up for me? 342. So the molecular mass of our molecule was 342. Grams or AMUs? If we had a whole mole of it, that 6.02 times 10 to the 23rd number of molecules, it would be 342 grams. But so if you had a mole of it. But if we only have an atom of it, it would be AMUs. Atomic mass units. Give me another one.
13.
13. All right, 1 liter of 3 molar sodium chloride has how many moles of sodium chloride in it? So when we were talking about molar solutions, molar, big capital M, is just shorthand for moles per liter. Moles per liter. So 3 moles in 1 liter would be a 3 molar solution. If I had 2 moles in 1 liter, it'd be a 2 molar solution. But to mix it up a little bit, if I had 3 moles in 2 liters, 3 divided by 2 would be 1.5. It would be a 1.5 molar solution. So you reduce it or change it or multiply it to make it over 1 single liter. Someone besides Maggie, give me a question. 14. It's over here. All right, so let's start by finding out the molecular weight, molecular mass of sodium chloride. So sodium weighs how much? I actually don't have that one memorized. How much? 23. 23. Chloride weighs 35.5. So adding that together is 58.5. Now that would be your grams in 1 mole. So the grams per mole. But we don't have 1 mole. We have 3 moles. So times 3. Can someone multiply that for me, please? 175.5 grams for 3 moles. So this was a 3 molar solution. So it had 3 moles in that 1 liter. So that gave us the 175.5. Good? All right, anyone have another one? 17. All right, that's a good one. as our, so for this one, we're starting off with, oh, that same big molecule. What was our molar mass for that one? 342. Same molecule? Yes? Yes. All right, so 342 grams per mole. I'll be able to solve it here. All right, so for 17, we don't have a full liter of this. We only have 300 milliliters. So we have 342 grams in 1 liter. Now, but we have to have the same proportion in 300 milliliters. So let's pretend this 1 liter is actually 1,000 milliliters, because 1,000 milliliters is one liter. What do I multiply, or how do I convert 1,000 milliliters to 300? What would I multiply that by? So this times something equals, how about times 0.3? Would that do it? Yeah. So times 0.3 will give me the 300 milliliters. All right. Can someone multiply this times 0.3? So whatever we do to the top, we do to the bottom to maintain that ratio. 102.6. 102.6. So we multiply the bottom. So when we're going from a larger volume to a smaller volume, we decide what conversion factor we're going to use, and we apply it to both the top and bottom so the same ratio is preserved. Good? All right, maybe one more, and then we'll start talking about the next stuff. How about balancing equations? So I think some of us are still got some hiccups on balancing equations. So I'm going to lead into this next topic, like our new topic. But I'm going to linger a little longer at balancing equations, because this is like the accounting of chemistry. You just have to end up with the same number of atoms on both sides. All right, so someone help me recall, I've already said it once, what is our magic number that makes up a mole? How many atoms does it take to make a mole? Don't all talk at once. Like, the uncomfortable silence is supposed to be a really good tool. How many atoms to make a mole?
Atoms to make a mole.
6.022.
6.022140076.
Thank you, Siri.
I'm so smart.
All right, 6.022. I get tired after the first two, but it's true. Times 10 to the, what was that number, Levi? No, without looking.
It was like 10 to the 23rd.
23rd. 10 to the 23rd. So that many atoms makes a mole. It's just like a dozen, or however many people are on a sports team, or it's just a fixed number. So how many atoms does it take to make 2 moles?
What was the question?
How many atoms does it take to make 2 moles then?
2 times that.
Yes, what's that number? When you multiply something that's to the power of 10.
To the power of 20.
Oh, whatever, you know what I mean. Listen to what I mean, not what I say. What would 2 of these be?
You just multiply the 6.022 and leave the behind it.
Yes, very good. 4. Times still 10 to the 23rd. All right. All right, so if sodium weighs 23 grams per mole, how much would 2 moles of sodium weigh? So sodium weighs 23 grams per mole. How much would 2 moles weigh?
46.
46. Alright, so if I put 46 grams of sodium in 1 liter, what would its molarity be? 46 grams of sodium in 1 liter of water.
2.
It would be a 2 molar solution. So 1 mole is this, 2 moles is 46. And when I put that in a solution, I end up with a 2 molar solution. How are you feeling about that? Give me a thumbs up, thumbs down, like a wiggle. I like the eyebrow effect. Heston, what do you think? All right, you want to do another one?
Sure.
All right, give me another atom. I only write down one example. Now I need one from scratch. Give me an atom. Carbon. All right, now y'all just memorize what carbon weighs. Like when you're doing like radiocarbon dating, they talk about carbon 12. So carbon weighs 12 atomic units. So 1 mole equals 12 grams, because I got that 6 times 10 to the, what number was that, Levi? 23rd. Thank you, Caroline. So 1 mole weighs 12 grams. I'm going to take my 12 grams of carbon out. I'm going to put it in my beaker. I have 1 mole of carbon. Oh, but let's do 3 moles. Can I put 3 moles in? How many will that be? 36. So my 36 grams is 3 moles of carbon. I'm now going to add 1 liter of water to it to bring it up to 1 liter. So over 1 liter of water, this will make
3 molar.
a 3 molar solution. Perfect.
So is it just more a memorization of like how many moles?
Well, you can always pull off how many grams in that mole of numbers. But as we're going to see going forward that you read about in chapter 10, our law of definite proportions. Does that sound familiar?
Yes.
Yes, because you read and took notes and highlighted.
You want to see this, girl?
I believe you. Look at you drew pictures.
Alright.
I know. See, that's a good way. Like taking notes is not natural. Pictures are good. You know, it says synthesizing material. That's why you're so smart.
Sure. If you say so.
You and your artistic nature.
Oh my god.
All right. So, what was I saying? Why do you distract me? All right. So, you don't need to memorize this. You need to memorize how many what a mole weighs, because you don't have to memorize it. You pull that off your periodic table. You just need to know where to find it. And how many moles in 1 liter. If you have 3 milliliters because you want to save product, you just multiply it by a conversion factor. But why does this matter? All right, because chemistry is all well and good to think about, but what if you're making something? Because, pure science doesn't make as much money as applied science. So, but someone would totally disagree with me if they were a researcher. All right, so what was I talking about? All right, so as we learned in the book, definite proportion. So we've been talking about a reaction in terms of atoms. So if we have a coefficient of 1 reacting with something else with a coefficient of 2, we have 1 atom reacting with 2 atoms to make your product. So reactants on one side, your products on the other. But now we're going to start talking about these things in moles, because we're going to talk about how much we're going to produce and how much we need. If we want to produce X amount, how much do we need to put into this? All right, so here is our first reaction I want you to look at. C2H5OH. Now, I wanted to just briefly touch on, because a lot of chemistry is organic, because lots of things in the world are organic. So whenever we have carbon, hydrogen, and oxygen, you're dealing with an organic molecule. Anytime you see a lot of carbon. Most of how organic molecules behave, it does not matter how many carbons there are. There could be 2, there could be 20. It matters these functional groups on the end. So we'll start seeing things like, in this case, it's an OH, which is an alcohol. So when we're talking about the isopropyls, the ethanols, the propanols, anything that has an all at the end is an alcohol. An OH, when we say alcohol, propanol. This one is ethanol. which is the consumable alcohol. All right, so let's react that. Let's burn it in our perfect oxygen environment. And we're gonna produce perfect combustion, CO2, and H2O. Now, as we were talking about last week before we left, we were looking at nitrogen and making nitrogen oxides. They're sometimes referred to as NOxes, because in reality, oxygen, our ambient air, is mostly nitrogen. And so it doesn't produce pure carbon dioxide and hydrogen or water, but that was just like a side note. All right, so we have our ethanol burning with oxygen, making carbon dioxide and water. So let's do our balance sheet. Is there something burning?
Yes. Burning like back that way.
What is it? Is this another, are we gonna have another fire drill thing in a minute?
Probably.
Okay. Yeah.
You should go visit.
All right. So when we're going to balance this equation, so we didn't dig into our exam because we're doing it now. We have our reactants and our products.
Yeah, I just want to know.
All right, so the things we started, so this is a little bit of my personal flavor on how I do it because it helps me. So you can see I have oxygen both here and here. I have two separate molecules that have oxygen in it. So I start with carbon, hydrogen, and I actually write oxygen twice because when I multiply this oxygen to something, I'll have to add them together to see how much I have all together. But it helps me see it. You can have just one oxygen as long as you can follow what you're doing. And so how many carbons do I start off with? How many hydrogens?
1,
And 6. So even though they're in two separate places, like you could have written this H2C6, but they're trying to show you that the OH is your functional group. That's going to dictate how it behaves. That's going to be the reacting end, essentially, of the molecule. And because it's in the same molecule, I don't separate it here. How many oxygens do I have in our ethanol? 1. And how much in our gas oxygen? 2. Our product side, how many carbons do we end up with?
1,
How many hydrogens do we end up with?
2,
So I have oxygen again in 2 places. So what am I gonna do? I kind of separate it. I don't know which one's gonna go where, but it's 2 different molecules and I already have it over here. As long as we end up the same. Okay, so I've got 2 and then 1 as a part of oxygen. So these do not balance. These are not the same. We cannot change these little numbers. This is what determines what the molecule is. We can only change big numbers in front. Those are what we call coefficients. So I'm going to tell you the answer because this is a lot of back and forth. And
Wait.
do you want to have it? Let's give Maggie a moment to figure it out.
No.
I know it's kind of like Sudoku. Like if you enjoy a puzzle,
Yes.
yeah, it can be fun. Or you can look up the answer. You just gotta be able to look at it and say, okay, they match. All right, so Maggie, just don't look. Why do I have an O there? This is supposed to be a 1. Write what I mean, not what I say. Alright, so this makes sense?
is not balanced.
It is not balanced. Why is it not balanced? Oh, let's talk about that. Alright, let's look at the carbon first. So carbon, 3 times 2 is 6. So if I put my 3 here, and 1 times 6 is 6. Alright, carbon's balanced. Yeah. Alright, so now on to hydrogen. 6 times 3 is 18. 2 times 9 is 18 as well. So if I have a 2 in front of this, it'll work out. I'm supposed to have a 6 in front of this one. I never plan well for spacing. Like, never. Alright, so this oxygen was supposed to have a 3, and this one was supposed to have a 9. So this 9 here, what goes in front of that? These 3 here go in front of this one. This 6 goes in front of this carbon, and this, hold on, that's not right. 9, that's my bad. Yeah, I'm gonna just scribble that out and write a 9 up. Yeah, this 9 goes in front of that water molecule. So our oxygens don't balance. This one's 9, this one's 18, but they're all oxygen. So our 3 plus 18 equals 21. And our 12 plus 9 also equals 21. So when you look at all the oxygens on one side and all the oxygens on the other, it does balance. So all I really want you to be able to do is count them. So noticing that the 6 times the no number here is 6 carbons. The 6 times the 2 subscript next to the oxygen is 12 carbons. Adding that together with 9 times 1 is 9, or this 9 times 2 on the hydrogen is 18. So this is your balance sheet, and each one ultimately balances, even if you have to pull from multiple molecules. All right, so up until this point, we had said if we had 3 atoms of ethanol would react with 9 atoms of oxygen, would produce 6 atoms of carbon and 9 atoms of water. So we are going to move on from talking about atoms reacting with each other and start talking about moles. Yes?
I got something different.
Because you did it wrong.
Oh my gosh. Or maybe I wrote it down wrong the first time. I don't know.
Yeah, I make mistakes. We can revisit that. All right, so now we're talking about moles. So you could, if we were talking about, you could triple this and say, 3 times 27, and you'd just have 3 times as much. But instead of talking about multiplying it times 3, we're multiplying it times 6 times 0.02 times 10 to the 23rd. So we actually have a sizable amount of material that we're working with instead of trying to imagine tiny little atoms. Questions? Tea break. Thoughts? Disagreements? Oh. Yes. You can go to the principal's office. All right, we're gonna move forward. Is it time for you to get in groups? Or are we doing on time? We're doing it on time. All right, here's another example. I gotta get rid of some extra paper. I'm gonna write on the back to save paper.
Yeah.
Is that too confusing?
Well, somebody opened the door. It was propped open earlier, so it's like coming into the room.
All right, I'm gonna see if this works over paper to solve it.
Would this also be right too?
I don't know. Let's see here. So you have 3. This all could be reduced. You're right. So all these could be divided by 3. Yeah. So this could be 1. This could be 3. This could be 2, and this could be 3. Is that what you have? Yes. And that's right. Thank you.
You're teaching us lies.
They're both right. That was just 3 times as much. Maggie is right. Don't tell her mother. Alright, I'm not going to try and balance that out. Alright, so here's your next example. Yes, really? Alright, so we have 3 manganese oxide, 3 moles this time, not 3 atoms, times 4 aluminums. Will produce 3 manganese and 2 moles of aluminum oxide. 3. Alright, how many moles of magnesium will you need to start with if you're reacting it with 1 mole of aluminum? I don't want to spend the money to react 4 moles of aluminum. I only have the money because I'm a manufacturing facility and I'm trying to reduce my overhead.
3/4?
So Maggie says, if I only have 1 mole of aluminum, I'm gonna divide this whole thing by 4. So which would give me 3/4 a mole of manganese oxide. Only 1 aluminum. I'll do the same to the other side. 3/4 manganese. And then 1/2 aluminum oxide. What do you think of that? So this is the law of definite proportions. The proportions of your moles, of the moles of your reactants to your products stay the same. Can we repeat that? Can someone just to make me feel like you're listening, repeat that, what I just said to Lucy? It just validate me. Validate that I'm not talking into the air.
Proportions, definitely. And
Definite proportions. So my question was, if I only want to start with 1 mole of aluminum, my reaction is based on 4 moles of aluminum. How do I change all the proportions? So to change 4 moles to 1 mole, I divide by 4. So I have to divide everything by 4.
it's like you're doing a recipe,
Yes!
and you have to either increase it or decrease it.
It's exactly like doing a recipe. Have you ever brined a chicken?
Huh?
Alright, we'll come back to that. Well, you make a solution of sodium chloride and salt and herbs. And you have to dissolve it, get to its solubility point, and you can increase it and decrease it based on size. And how many cookies you want to make or chickens.
Yeah.
Alright, so what if I start with 1 mole of magnesium oxide? How much, if I only start with it, how much aluminum oxide will I make? What will I divide it by?
3.
I will divide everything by 3. Which will give me how much aluminum oxide?
4/3.
I'm starting here. Not, so,
2/3.
2/3. 2/3. 2/3 what?
Aluminum oxide.
2/3 aluminum oxide, what's my units? 2/3 a gram, 2/3 an atom, 2/3 a mole. Now, if I knew off the top of my head how much aluminum oxide weighed, which I do not, I would multiply that molecular mass times 2/3, and that would tell me how much aluminum oxide I am making in grams. So your leap here, so this last week's reading was about the definite proportions. This week you're going to working with grams and seeing how we actually are going to touch the stuff, to make the stuff. All right. I'm not going to ask you this. All right, so we ready to get in groups? All right, we're going to start with, no, not yet. All right, one more thing. Simplest equation. I have carbon, I have dioxide, oxygen. I make carbon dioxide. So this is balanced. If I start with 24 grams of carbon, and I react it in excess. Do you remember me using that language way in the beginning? It means so much it doesn't matter. When you set something on fire in here, you don't know how much oxygen. Or, like, again, isn't it so convenient that they demonstrate whoever's burning the stuff outside? He doesn't have to measure how much oxygen he's using because there's plenty of it. So I'm just saying in excess. I'm going to start with 24 grams of carbon, reacting it in excess oxygen. How many moles of carbon dioxide is produced?
2.
Do you want to explain why?
So 24 grams of carbon equals 2 moles of carbon.
So in this reaction, we show our proportions. For every 1 carbon makes 1 carbon dioxide. So when we start with 2 moles of carbon, that molecular mass you just memorized is 12 moles per gram, grams per mole. So this is 2 moles So when we have 2 moles of carbon, we're gonna make 2 moles of carbon dioxide. How much would 2 moles of carbon dioxide weigh? Oh, 12 plus 32. That's for 1 mole. What's 12 plus 32?
44.
44. So how much would 2 moles weigh? 88. So your 2 moles of carbon dioxide is gonna weigh 88 grams. I told you we started with 24 grams of carbon dioxide. Conservation of mass tells us that we're neither creating or destroying material. So we are making 44 grams. We started 24 grams. How much oxygen in mass did we use? This number here. What would you think?
32.
32, does that add up to 88? No, it doesn't. So I'm asking for the mass.
64?
Does 88 minus 24 equal 64? Yes, it does. doesn't
Yes, it does.
Okay, 64. So 64 is also 2 grams, 2 moles of carbon dioxide. 1 mole is 32 times 2 is 64. So not only do our atoms balance, if I am only making pure product and I have a completely perfect reaction, I will have my atomic masses on one side balanced with the atomic masses on the other. Yay! Look how perfect it is. Don't you love the symmetry? Yeah. All right, let's get in groups. I'm tired of talking to you. So if I collected less than 88 grams, by the way, it means my reaction either wasn't complete or I created byproducts like carbon monoxide, nitrogen oxides, something else. Probably just carbon dioxide. Oh, am I no longer filming?
No. I mean, you are.
Okay.
No,
Let me show you your last reaction. And then you are going to get in groups of 2 or 3 and work on this. So our reaction is potassium plus water. Leave enough space to add your coefficients. I always forget that. Goes to KOH plus, what else? Oh, that's it. All right, so my potassium water goes to KOH. Step 1, balance the equation. So get in groups and balance your equation. Step 2, calculate how many moles in 10 kilograms. So I'm going to give you 10 grams, of potassium. How many moles?
Is it not already balanced?
It is not balanced. You will have to balance. No, it is balanced. You're right. Good job, Maggie. It is balanced. No, it's not. Oh, hold on. I'm missing something. That's why. It is not balanced. Okay. I have 3 hydrogens. That was what was missing. All right. So how many? I'm giving you potassium. 10 grams of potassium. How many moles is that? Then I want you to know from that reaction how much KOH is formed from that reaction. How many moles of how much KOH, potassium hydroxide, is produced first in moles and then in grams. So how many grams of H2? H2. And then I want H2, how much H2O? Do I have enough? I'm sorry, it is H2O. Let me make sure I wrote this right. So potassium reacted with water makes hydrogen gas and potassium hydroxide. This is your correct equation. You're given 10 grams potassium. How many moles is that? Then how much are you producing in mass? You'll have to go through moles of potassium hydroxide and hydrogen gas. And then find out how many grams of water you needed. Grams of water you use to react with your 10 grams of potassium. And then ultimately I want you to find out if your equation balanced in mass, if you end up with the same mass on both sides. The masses are equal. I would like you to use 3 significant figures when you do this. When you find your answer at the end, you might have 2 decimal points, but I want you to look at that and go back to 3 significant figures. So when you take your molecular masses, 3 significant figures. So we have, let's say 14 minutes. Can you get in groups of 2 or 3 and work through this? First step is to balance the equation. So work to the person directly to your left, and you guys, why don't you work with Hesed and Levi then?
So it's just like a whole, that's like dominoes. So,
It's not strict.
I guess to make sure.
alright, so if we change the age over here to, wait, we can't go out. So, 2 from here, and 2 here, so it's 4. There's 5. So, actually, you're not gonna, so, oh, sure enough.
Yeah, let's just kind of back.
So we know we have.
This is Jillian. Jillian is not here, and Grayson is not here, and Mike is not here. But Micah was out last week.
Then you have to also balance out, but also make the
Julie, here's more papers.
I'll take my.
Oh no, these are the ones. These are absent people.
Oh, that's 8.
So if you're getting a number that is divisible by everything, like exactly what you corrected on the other. So if everything's divisible by 2, divide everything by 2. Oh, that's a 2 though. Yeah. Sorry. You're good.
She just graded it. I just turned this on.
So are we saying, because of that, we don't have to put anything from this? Yeah. So that's why I was wondering why there was a blank in front of it. Yeah, it's just fair to do that, I was kind of sure for all of this. I think it's the whole.
So we have 6 options. 4 plus 4, because now there's 4 Ks, so that's 8 on both sides. That's 4 Ks on both sides. And it's 4 on both sides.
Alright, we jump into how many moles.
Yeah.
If you want, you just tell you if you're on the right track.
Gotta make the oxygen
Yeah. So how many grams per mole of potassium? What's the molecular mass of potassium? I don't remember. Oh, I wrote it down in my notes. I'll tell you. No, I think I forgot. I didn't put the decimal. I just wrote 3 numbers. But do it to 3 6
I might have gotten
He's not here to fight. I think it's. Alright, potassium, 3 minutes. I think it's 39.1. So how many moles is 39? Is 10 grams of the weight 39.1 grams per mole?
39.
That's what I wrote down. Is that right? I make mistakes.
Is that the same?
Here is a pull-out. Potassium is 39.1 grams per mole.
Okay,
Well,
So your next thing is to find out how many moles is in 10 grams. So you have 10 grams.
yeah, that's grams. That's
Times,
so 39.
The 10 is, so it's 10 grams per mole.
39.1. So we can cancel to 1 mole. So 10 divided by 39.1 will give you how many moles, that small fraction. So you can see that 10 is smaller than 39.1. So it's got to be less than 1 mole.
Maybe not 3, we have to add. That was what we did, we had that H2. I don't think there is another way.
10 divided by 3.91.
But it might not be 3.
You need a calculator.
So 3.
Hey J-Boy, Johnny James, get your backpack and come sit. Or you can sit there, but get your backpack and your water bottle.
39.1.
Oh, does that still need to be?
What'd you get? 0.25. Three significance figures.
255.
Yes.
You could probably start.
What's the number after 5?